Yes, yes, I can see your screen.
Okay, because I got here the two screens and I don't know which one of the two is broadcasting. So my name is Eric de Bat. We are working, as I already mentioned, in Europe and in Argentina as well. We developed an unmanned aerial service for agriculture. Where is this positioned? It's in the first part for the data collection, next to satellite imagery and in-situ sensing mounted on the tractor or with SPAT to find in the field corrections on which you can apply on your crops. We have the unmanned aerial vehicles. Later on, at the end of the presentation, in fact, we will compare this method with the other ways of data collection and how it can be complementary to you. Now, the second step is the data processing. As I already mentioned, we have to make indexes, we have to make a task map. It will be distributed over the internet to the end user. For UAVs, we have one extra step, and that is making the picture, because flying over a field while the UAV makes the pictures, you end up with about 300, 400, 500 pictures which need to be made into one map, like stitched them together, so you can get your multispectral picture of your field, geo-referenced as well. So here we have a picture of the vehicle, the yellow one over here. But in fact, we speak about not unmanned aerial vehicle, but unmanned aerial system, because it's not just the plane, it's also the computer with the ground station. It's the software to plan your flight, to maintain the link with your plane, because it goes as far away, you don't see it anymore, you don't hear it anymore, and you just have to trust that it will come back following its waypoints. So we also need to have safety measures, so in case something goes wrong, that the plane at least comes back, and if it gets down, that you can find it back again. But normally, if everything goes fine, which is now the case, this plane flies 45 minutes at an altitude of 250 meters, which means that you can fly 300 hectares in one flight at 15 centimeters resolution. This depends, of course, on the camera. Later on, I will give some more information on the camera we are using. Now, then, about the plane itself. It's the one you can see here. We have designed it with our team in the Netherlands, and we are constructing it here in Argentina. And it is especially designed to fit the needs of the agronomist and the farmer. Why is this? For the flight characteristics, because in one flight, to fly 300 hectares, that's about a good size to fly 1 or 2 fields. In Europe, maybe here in Argentina, it's just enough to fly 1 field, and in the US for sure as well. But of course you can do more than 1 flight, that's not a problem. It's electric, which means you don't need to have fuel. It's very easy to handle because you just have to switch the batteries. You don't also need to have too much knowledge about aeromodelism, because this one has an automatic takeoff and landing, and it is customized to operate with these multispectral cameras, which we have a look at right now. The camera we are working with is Tetracam. It's a company located in the US, in California, and they make lightweight multispectral cameras. The one you can see here has 6 lenses and weighs only 600 grams. Here you can see the lenses we have mounted on it. It's the blue one, the green one, and the red one, which gives you the true color composite, the regular colors. Then below we have two near-infrared ones, which is in fact one of 690 nanometers and another one of 710 nanometers. And the last one is the infrared one. This is the infrared picture, and this is the one combined with near-infrared. We can put any filter on it. But we are flying now more than 2-3 years with this camera, and we found out that actually for agricultural applications we have enough with just 4 lenses. And now we'll get into detail which frequencies we need for actually all applications for agriculture. Now here we have an example of a mosaic of a field in the Netherlands. We have flying this one the 30th of June in this year, 2 months ago. No, less, 1 month ago. So here we have a combination of the red edge with the green one. Now, these two bands give us an indication of the nitrogen content in the plant. On the left-hand side, you have a maize field. It's a test field with different levels of nitrogen fertilization. You can see clearly the differences. The lighter parts are differences in biomass. And on the right-hand side, we have a potato field. The gray parts is lesser grow due to it has been raining a lot in the Netherlands lately, so these areas were a bit flooded, so not too much crop came out. But the dark spots here and here as well, and this row as well, this is experimental. We did some extra fertilizing to the crop to try to see the differences and to detect at what values in the spectrum will give us an indication of a known amount of nitrogen in the plant, and perfectly detectable in any index you can make using red edge and green. Indexes you can use is T-carry, M-carry, just some examples out of many. The same flight with the camera, we made also the red imagery and the infrared, and these two give an indication of the biomass. As that I've explained earlier, with these two bands we make the NDVI or other vegetation indexes that give us an indication of the biomass. All use these two bands. So here it's the same field at the same date, and you can't see here anymore the different nitrogen levels because the biomass is still the same. What is different is the nitrogen content in the plant. So probably later on the season, around now, we don't have an image now, but for sure we will see the differences in the biomass and not anymore in the nitrogen level in the plant because it has been absorbed and transferred into biomass. Well, that day we have also flown over a field of winter wheat, which is of course sown before maize and potato. And here on the left-hand side, we can see again the image with a combination of green and red edge, which gives an indication of the difference of nitrogen level in the plant, and we almost see no difference. While on the right-hand side, we can see here these two rows with extra biomass. And these were the areas where we had the test plots where we have put extra fertilizer, not visible anymore as nitrogen in the plant, but only visible as extra biomass. So this is a way we are now investigating on how we can relate the imagery with the small band spectral lenses to a concrete application in farming. So another example here is this field, also a test field these are the different nitrogen levels of fertilization, biomass differences, and temperature differences, because we are also able to put a thermal camera on it. This has several advantages using thermal imagery. On one side, we can detect irrigation, water stress problems. On the other side, it's this is something we want to test this year here in Argentina to detect plagues, especially in soybean, because when there is a plague in the plant, you can't see it directly in the NDVI or in the greenness of the plant, but the plant stops to evapotranspirate, which makes that the plant is heating up, is getting fever. Like humans do, the plant also gets fever and heats up. So this would be a way to for early detection of plagues. Well, now we have these maps. We can detect nitrogen. We can have an idea about biomass, about the water stress. What can we do with these imagery? How can we transfer these maps into an application for the farmer that he can use on his tractor? Now, last year we have flown over this potato field in the south of the Netherlands, and we made this biomass index. It's called WDVI, which is a variation on NDVI. It's corrected for the soil because sometimes high NDVI values, it gets too saturated, and this will reduce a bit the value so we can keep on measuring furthermore in the season. So we have on the left hand side we have an image of the 28th of June, and on the right hand side 16th of August. So the WDVI has dropped a lot because now the plant is investing its energy in the potato and not anymore in the leaves. So we need to do some potato hole killing, which is killing the leaves. So what we did is use this WDVI map, this biomass index, to make a task map. So here every color means an amount of liters per hectare of herbicide, and it has been applied on the field on a variable rate. For the first time in the Netherlands, we have been able to do this. Why? Because the timing is so important. And Netherlands, maybe more than other countries, maybe comparable to England, is very cloudy. And the satellites, they couldn't acquire the image when the farmer was needing the image. So the solution was to use UAV imagery, and we made this map on a cloudy day because you can fly at 250 meters, which is under the clouds. And we have been able to make this task map flying 4 days before the application of potato haulm killing last year. Another example here is for fertilization with nitrogen. I don't know how it is in other areas, but in the Netherlands they try to fertilize now 2 times a year. Half, 50% at the beginning, and halfway another 50%. So initially, without really knowing about the variability in the field, they throw 150 kilograms of gas per hectare everywhere. Gas is a fertilizer. So now, with this UAV image, we can see the equivalent of how many kilos per hectare is still available in the plant of nitrogen. And based on what is available, we can make the difference map, because according to the experience, we know that the second application fertilizers should be around that the required level of nitrogen in the plant should be around 120 kilograms a hectare. So we can, knowing what is available, we can make a variable rate task map. So where before we should throw 150 kilos per hectare everywhere, now it is 50 in the north, 40 kilos in the middle, and no extra fertilizer in at the lower part of the field, which means, especially in terms of money, a big difference, but also for the environment, of course. So then, one special feature of the UAV imagery is the resolution. Now, in the US and here in Argentina as well, it doesn't really matter this resolution because with 5 meters or even Landsat imagery of 30 meters for 1 pixel is more than enough if you want to have an idea about what is going to be the yield of your field. But we have now the possibility to see other things that before we didn't even think about what that could be an application of the imagery. As Ed already has mentioned before also, is that we can identify problems with the equipment. As you can see in this map, which is also winter wheat, we can see the different lines here. Here this lighter line and this darker line. There are differences in the spray. Here, this is the lighter line. Here is a broken spray on the fertilizer machine. Another interesting part here is that the stripes. We have extra biomass here, in fact, and lower biomass. Extra biomass, lower biomass. Why is this? When the machine drives by over this line, the arms of the fertilizing machine were moving too much because the machine was driving too fast. So we have extra fertilizer and another part no fertilizer. So yeah, you can see here one deficiency due to the equipment, and another one is due to the driver of the machine, who was driving definitely too fast. So what other kinds of things we can do with this imagery is damage classification, salinization monitoring. We can see plagues because of the high resolution. So to finish, we can quickly have a look at the advantages of the different complementary platforms, which are satellites in this case for imagery, and our UAV, or any UAV in fact. Well, we have full control over the acquisition time. We can choose the spectral bands, which we know now can be reduced actually to 4, being the green band, the red edge band, and the near-infrared band, and optionally a thermal camera. Flights can be done underneath the clouds, and of course we have the highest spatial resolution possible. The advantages of the satellite platform, which can of course can never be equalized, are the area. Satellite has very large areas. Like with UAV, we can do just one field. And then we also have the geometric correction with the UAV. You have the part that you have to make the mosaic and joining hundreds of pictures, which can be now quite automated. So that's not that much an issue anymore. So I hope you have learned something about the use of UAVs, possibilities we can have it with it, and I think within the future it will be one more tool in the precision agriculture service chain. Thank you very much.
Well, thank you very much, Eric. That's very interesting.
Okay, thank you.
Well, if I may add, we've been following this, and we worked with Eric's company last year doing yield prediction and also doing protein estimation in wheat. And well, we're seeing it evolve very fast. So I think that we'll be seeing more and more in this season and next seasons. There's one question, Eric. I will unmute. It's, can you measure biomass in a wheat field that is just prior to harvest? From Jessica.
Sí, Pablo. Bien.
I think Eric is. I'll get it for Eric. Jessica, yes, that's exactly what we did in experience with Oria imaging. In fact, It's for it was for a large food company called Molinos, a little bit like Kraft, Orlando Lakes in the U.S. They have their own wheat fields. They produce their own wheat, and they need to have high quality wheat. So they use this to correlate other indexes with chlorophyll content, and it gave very good results. They applied late fertilization, and they were also able to correct some of the protein levels. So I can send you more information about that. And you can measure biomass in a wheat field. They use that also for yield estimation. The experience that I was showing in yield estimation, in fact, was from that company. Okay, so